Hello there, Mr. Sutton here, bringing you the Pre-Cal Honors 8-2 lesson on geometric series and sigma notation. In this one, we will be finding nth terms for geometric sequences, finding sums of finite geometric series. We'll deal with the infinite ones another time, and we will also be using sigma notation to basically add stuff up. To start this one off, let's take a look at this sequence. Now, looking at this, you're going to notice right away this is not an arithmetic sequence. We're not adding the same thing to get the next number. Instead, we are multiplying to get the next number. So this is an example of a geometric sequence, which is a list of numbers that have a common ratio rather than a common difference. Because we're multiplying by the same thing over and over again, we don't have a linear pattern anymore. Now we have an exponential pattern. So pause the video and see if you can remember how to find the 13th term of this sequence here. So for this, we're going to need our geometric nth term formula, at least if we want to do it quickly. So we're going to be starting with the first term, a1, and now we're going to be multiplying by a common ratio over and over again. So we're going to need an exponent on this. And because we've already used up the first term with a1, this is going to be an exponent of n minus 1, kind of like with the arithmetic sequence formula. So plug in stuff in. We have an a1 value of 2, and the common ratio, what we have to multiply by to get the next number, you can just do the second term minus the first term. So 6 divided by 2, or 3 in this case. Multiplying that out, we've got 2 times 3 to the, in this case, 13 minus 1. And now we need the calculator. So plug in all that in. We end up with, let's see, 1,062,882. For our next example, we're going to shift gears here to try to find the sum of a geometric series. So a geometric series, this is just the sum of a geometric sequence. For example, for this one, we want the first 11 terms added together of a sequence that starts with 6, and then we're multiplying by 5 each time to get the next number. So we've got 6 plus 30 plus 150, and so on until we get to the 11th term. Now, as luck would have it, there is a convenient formula for adding up a geometric series with n terms. It is this formula here, which I'm not going to try to explain where it comes from. So we've got a1 times 1 minus r to the n over 1 minus r. First term, common ratio, number of terms. Pause the video and see if you can use this handy-dandy formula to figure out this sum. All right, so we've got a1 value in this case of 6, 1 minus 5 to the 11, that was n in this one, all over 1 minus our common ratio of 5. And now it's time for the calculator. Now in this one, I always use alpha y equals for that little fraction format. It saves me PEMDAS issues. Pressing enter on this, it looks like 73,242,186. For our next example, we're going to do a little real-life problem. So for his salary, a king's advisor wants 1 grain of rice on the first day of employment, 2 on the second, and 4 on the third, so we're doubling each day, until an entire chessboard is filled. We want to know how many grains of rice the king is going to owe his advisor when all is said and done. So we're basically asking for the sum of a geometric series, because we have a common ratio here. So we're starting with 1 plus 2 plus 4, so on and so forth, until we get to that 64th square. That last term is going to be 2 to the 63rd, because that first square was 2 to the 0, so it's 64 minus 1 there. So pause the video and see if you can figure out how much rice the king owes his advisor. All right, so there's our formula for the sum of a geometric series again. We've got our first term of 1. Common ratio in this case we said was 2 because we're doubling each time. And n in this case is going to be 64 for the 64 squares on the chessboard. So plug in all that in. Let's see what that comes out to on the calculator. And the calculator says about 1.845 times 10 to the 19th power. Very big number. Suffice it to say that it would take the world at present production levels about 926 years to make that much rice. So I'm not sure the advisor's getting the job. At this point, we're going to shift gears to talk about different ways of writing out series of any kind. So there's actually 2 ways to write out a series, in expanded form or summation sigma form. You've been using expanded form this whole time. It looks something like this. It's basically all the terms of a series just written out. Now, another way of writing this, especially if you have like hundreds of terms, is using something called sigma form or summation form. So this form has a few different parts, and by the way, this is the Greek letter sigma, or S, it's for sum. So the different parts of this formula in here, this 3n, is called the summand. This is a formula that tells you each term in the series. So this is like 3 times 1, 3 times 2, 3 times 3. Now, this formula by itself is not enough to tell you all the terms. We need to know what number we're starting at for plugging in and what number we're ending at. So that's what this 1 and 5 here are doing. These are called the limits of summation. These are the first and last numbers to plug in. And by the way, all the numbers between 1 and 5 that we're plugging in are going to be integers, so you're not doing like 3.6 or anything crazy. And there's one more important piece to this sigma form. It's this letter here, this n. This is called the index. This tells you what the variable in the summand is, which is important because if you also had x's and i's and some other crazy things in there, it's nice to know what letter we're actually plugging all these numbers in for. For the next few examples, we're going to try to evaluate some things that are in the sigma form of a series. So find the sum if possible. If it's an infinite series, we're going to write the first 4 terms instead. Let's try this first one out together. So the general idea here is starting with your lower limit, you're going to plug each integer, each number, into the summand until you reach the upper limit. So we're going to do 3 squared. That'll give us our first term when we expand this. Plus, now we're going to do 4 squared, and so on and so forth. Pause the video, see if you can finish this one. So we got 5 squared plus 6 squared, and we know to stop at 6 because that's our upper limit of summation here. Now just simplify if possible. So this is 9, 16, 25, and 36. So this is 25, 25 is 50, plus 36 is 86. So that's what this would evaluate to here. Now go ahead, pause the video, and try out this next example. So we're going to start with 2. Plugging that in, we have the square root of 2. Next, we have the square root of 3 plus the square root of 4 plus the square root of 5. And what are we supposed to go up to on this one? Oh, infinity. So we can't go that high. We're just going to write plus dot dot dot, and people will know that we're going to continue the same pattern forever. We're going to start this next example together. So just like before, we're starting with our lower limit, plugging it in here until we get to the upper limit. So we've got 6 times 5, which is 30. 6 times 6 is 36. 6 times 7 is 42. And we see there's a whole bunch of other numbers we're going to end up plugging in all the way up until 6 times 50, which we know is 300. I'm just going to put a plus dot 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 plus 300 to show there's a bunch of left out terms there. But this gives us a bit of a problem because these are constants. We're really supposed to add all these together and simplify it, but there's a whole bunch of them. So this is where, if you remember those special series we learned about, the arithmetic and the geometric series, if you recognize one of these as you're writing one of these out, you can actually use those sum formulas instead of adding things by hand in this expanded form. So for example, our arithmetic sum formula for this one, do you remember what that was? Oh yeah, that was n times a1 plus an over 2. So why don't we just use this instead? So that'll be, we got 30 plus 300 for a1 and an. And now just be careful picking out n. How many terms are there in this series? Well, from 5 to 50, that's going to be 46 terms. So that's going to be 46 times 30 plus 300 over 2. Let's do that on the calculator. And this one's going to come out to 7,590. So keeping in mind that some of these sigma forms are really special series in disguise, try this next one out on your own. All right, so I'm going to start writing out this one just to see what I'm looking at. We've got 1 over 8 to the 1, 1 over 8 to the 2, or 1 over 64, 1 over 8 to the 3, which I don't really remember what that is, and, oh, there's a whole bunch of these. I'm going to be adding everything up to 1 over 8 to the 32nd power. All right, so what's a faster way of doing this? Well, we know this is a geometric series. We have an a1 of 1/8, and also a common ratio in our value of 1/8 to get the next term. So I'm going to use this formula again. We've got 1/8 times 1 minus 1/8 to the, how many terms are there? There's 32 terms from 1 to 32, all over 1 minus 1/8. And this is a huge mess. On my calculator, I'm going to use that fancy fraction form to enter all of this now. So here's what it all looks like on the calculator if you use alpha y equals to get that fancy fraction form. And that all comes out to 1/7. Aren't calculators nice? Now you could also make this a decimal if you wanted. It comes out to about 0.143 if you round it off. For the next several examples, we're going to take an expanded series and put it back in sigma form. So I'm going to start on this one by just writing out a sigma because I know that's what my answer needs to have in it. But now to figure this out, it's good to take a look at your terms and see what's the kind of the common pattern for all of these. If you look at all these terms here, these are all multiples of 8. So I'm going to start by writing my summand here. If I want a formula that gives me multiples of 8, I should probably just do 8 times n. I also need my lower and upper limits of summation here. So 8 times what would give me my first term here of 8? Oh, 8 times 1. Can you figure out the upper limit of summation here? Well, we need 8 times 4 to get 32, so 4 is the next one here. So using what we did on this last example, see if you can pause the video and figure out a sigma form for this next series. All right, now in this one, starting with sigma, I'm not really sure right off the bat what the formula is, but noticing this plus dot dot dot, I know my upper limit of summation is going to be infinity. This is going forever. But now let's figure out that formula. These, it looks like, are all powers of negative 1/5. We keep multiplying by that to get the next term in the series. So I'm going to put negative 1/5 to the n power inside my summand here. But now I have to figure out my lower limit of summation. What do I have to raise all this stuff to? What n value to get 1 for my first term? I need the 0 power, so I'm going to write n equals 0 for that first one. And then if you plug 0 in, we get 1. If we plug 1 in, that'll be negative 1/5. Plug 2 in, that's positive 1 over 25. So it's not a bad idea just to go back and see if you can generate the first 2 or 3 terms after you think you've got your answer. We're going to tackle this last one together because it's kind of weird with these x's in here. So we know that this last one, we're going to have a sigma, and again, the dot 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 at the end tells us that our upper limit is infinity. But what about the rest of it? So to get these x's, the deal with these x's, when you have non-index letters in your summand, those are actually going to hang around as constants when you expand a series. So if you see an expanded series with letters in it, it means that those were non-index letters that were inside the summand. So that means we need an x in here to generate these x's. And we also need an index variable that is not x. So what else is going to go in here? Well, we have something times x to the same something all over those things plus 1, right? So we have a 3, a 3, a 4, we have a 4, 4, or 5. So we can write this as n times x to the n over, what do you think should go down here? Oh, n plus 1. So this is a formula that can give us all of these different terms. Now the next piece of this is our lower limit of summation. What should we start with for our n value? Well, we need to have a 2 in order to get the 2x squared over 3. So we'll let n equals 2 be our lower limit of summation. That's it for this one. Hopefully we've expanded your horizons. Till next time, Mr. Sutton signing off.